Okay, so we're going to do a couple of examples of finding a line integral along a curve in a vector field. But first, I want you to try, based on what you've learned so far, to answer these two FAQs. So number one, do you think if we change the direction of the parameterization, that the line integral of the vector field will change? And number two, do you think if we change the path between 2 points, that the line integral will change? Give your vote. And then we're going to do an example. We're going to come back to these to discuss. Okay, so here's our example we're going to start with. Here I have this vector field is shown in both pictures, same vector field. In both pictures, I have the same starting and ending points. We start at 0, 0, we end at 1, 1. The difference between these two is the path that we're taking through the vector field. And so I want you again to vote in your head. Do you think we're going to get the same answer when we calculate the work done along the green path as we would along the red path? Same or different answer, and why? Okay, let's try it. So I'm going to do along the green path with you, and then I'm going to leave you to try the red path, and we'll come back and compare. So we're going to calculate the work. Let's zoom in just along the green path since that's where we're starting. I'm going to calculate the work that's done along this curve. Okay, so we've shown that to find the work, I'm going to be doing a line integral over my curve, and I can write it. I have 3 different shorthand notations. I'm just going to write it as f dot t ds to remind us that I'm just going to remind us exactly where this comes from. You don't have to write this every time. But my t is really my velocity divided by the speed, and then ds is the speed dt. So at the end of the day, I just need to integrate f dotted with v dt. And let's get our units here. So I'm going to have t in this case, well, let's say a to b in general, but then we can see what we have in ours. We need to parameterize our curve because we're going to change variables. This is actually part of the changing variables. I would say that happened actually right up there. Okay, so to do this, I need to parameterize this curve, and it's moving along this path here. And I guess I didn't even tell you. Oh yeah, it's y equals x squared. Here you go. So we can easily parameterize that like we learned in chapter 10. It's an r by just letting x be t. And then that means that y will be t squared. And in this case, t is just going to go from 0 to 1 because it's only that part of the parabola. Okay, and now I'm going to use that to find v of t, which is just 1, 2t. And I'm going to also use that to help me simplify what f is. So f, my force field, starting out, is 3x minus y, and then x. And so if I'd like to rewrite that in terms of time, then I'm going to write that as f of r of t. And so that's going to become the vector 3, and then instead of x, I'm replacing it with what x is in my parameterization, which is just t. Oops, let's do colors so you can see. And then minus y, and y is t squared in my parameterization. And then I have comma x, but x was just t. So I'm literally just plugging in the fact that this is x and this is y in my parameterization. Okay, now all I need to do is take the dot product between this, my vector field f here, and my velocity over this curve and add it up. So let's do the line integral. This means my work is going to be the integral from 0 to 1 of the dot product. Let's write the vectors in here just so you can see. This is F dotted with V, and then dt, which is just going to simplify. So when you expand all that out and you just do the integration, we end up with 11/6. If we were thinking of this as work, and if our force had been given in newtons and our units in meters, then we would say this is 11/6 joules that's done by this vector field along this curve. All right, so take that idea, put it on pause, and then see if you can recalculate what the work done will be along this red curve given in part B. Okay, so now you notice we're going to have a different parameterization. An easy way to parameterize y equals x is just t, x is t, y is t. I still have the same 0 to 1. That's just a coincidence on this problem based on how I parameterized. My velocity then becomes 1, 1. My vector field f now becomes 3t minus t and t here. So when I take the dot product of that with the velocity field, I'm just left with the integral of 3t, which is going to give me 3/2. So I actually get a larger amount of work done when I'm going along this curve as compared to this curve. And so this is going to help us answer one of the questions, which is up above. If we change the path C, does the line integral of the vector field change? In this case, it did change, but it's interesting because it is going to depend on the vector field itself, and we're going to see why. Some of you maybe have thought, no, it should be the same because work shouldn't matter on the path, about the path. It should just depend on the starting and ending points, and that's going to be true in certain vector fields, not all. So that's why it's going to depend. In this particular vector field, work was different depending on the path. So we call that not path independent. Okay, the next piece I want you to try or talk about is down below, and I'm just going to put it all up here. If we let C be the curve given in part A, when we write negative C, we mean the same curve as C, but oriented in the opposite direction. And so I want you to notice what will happen with the line integral if we started instead at 1, 1 and went to 0, 0. What's going to happen is this is going to affect your unit tangent vector. And everywhere along the curve, my unit tangent vectors are now going to be pointing in the opposite direction that they were. And so when you take the dot product, you would expect your answer to be exactly the negative of what you had above. And in fact, that's what we'll get. And you could try this by just parameterizing the curve, or reparameterizing and redoing it, starting at 1, 1, ending at 0, 0. But it's not necessary to do that. We can just say, because we know the unit tangent vector is going to flip exactly 80 degrees, or 180 degrees, that we would expect this line integral to have exactly the opposite sign as the answer we got. So that goes back up to here. If we change the direction of the curve, the line integral will change. It'll be the negative, what we had. And this is to contrast what we did last lesson when we were just doing line integrals of scalar functions, not vector fields. We did a scalar function, like we were thinking of the area of that windy fence. The direction that we parameterized didn't change that area. We didn't get a different answer depending on our direction. And if we change the path between them, we would get different answers back with the line integral of a scalar function, as opposed to what's happening here with vector fields, where changing the direction gives us the opposite sign, and changing the path sometimes won't change the answer, and sometimes it will. We're going to come back to that. So that's all for this lesson, and then we're going to move on next lesson to line integrals and surface integrals involving flux.